Hello, and good evening. Good evening from Sydney, Australia, and welcome to the October 2021 meeting of Skeptics in the Pub. My name is Richard Saunders from the Australian Skeptics and the Skeptics Zone podcast, and behind the scenes, working very hard, is Lara Benham making all this happen. Before we begin, I would like to acknowledge and pay my respects to the Gadigal people of the Eora Nation, the traditional custodians of the land from which we are broadcasting tonight. I'd like to pay my respects to their elders, past, present, and emerging. Now, don't forget you can subscribe to our magazine, The Skeptic, celebrating 40 years of publication. In fact, you can access most of the back issues for free, yes, free, at skeptics.com.au, and that's searchable too. And put next Thursday, or the next Thursday, the first Thursday in November in your diary, and that'll be Thursday the 4th, for the next Skeptics in the Pub online. And keep an eye on our Meetup page for more information if you go to Meetup and search for AUST Skeptics. Now, this year, the Australian and New Zealand Skeptics are holding a joint convention. That is on the 20th and the 21st of November. You can register at skepticon.org.au, and we have a great lineup of international and local speakers, including Dr. Susie Wiles from New Zealand, Professor Richard Wiseman from the UK. Please join us no matter where you are around the world. It promises to be a really, really good convention this year. We've never had a joint convention between the two countries before. We're really looking forward to it. And you can buy your tickets right now. Owing to COVID, sadly and luckily, it is online. Sadly, because we'd love to see you in person, but lucky for the rest of the world, because everybody can join in on the fun. But now, tonight's talk. We're going to be looking into the stars. Professor Geraint Lewis will talk about rare or everywhere, intelligent life in a hostile universe. Two possibilities exist. Either we are alone in the universe, or we are not. Both are equally terrifying, said Arthur C. Clarke. It feels like we're living on the cusp of one of those times where humanity's most extraordinary existential discoveries is about to be made. The proof that we are not alone in the universe. Since the report of alleged microbiological fossils on a Martian meteorite and other things, you may be familiar with the wow signals coming from space that Carl Sagan talked about. Are we about to enter a golden age of discovery regarding alien life? Now, despite what some people may think, Australian skeptics and skeptical groups around the world are quite open to the possibility of alien life. We don't think it's been visiting Earth just yet, but we're not saying it's not out there. So are we alone or aren't we? It's hard to underestimate the consequence of answering this question for the collective human soul, and it is for this reason the astronomers, the self-appointed gatekeepers to this universally fascinating search, demand a very high bar for such a claim, and so they should. Tonight's speaker was raised in Old South Wales with a passion for astrophysics and spends his time unraveling the dark side of the universe. His most recent book, Where Did the Universe Come From? And Other Cosmic Questions, was published in September 2021. You'll have the opportunity to ask questions of our guest, and you can do that via the link that will appear on the Twitch page you're watching now. Just type !Q into the chat. That's the ticket. Do that and you'll see the link, which will take you to our Slido page. And if you haven't already done, click the follow button so you'll be notified next time we go live. But for now, sit back and please join me in welcoming our guest speaker tonight, Professor Geraint Lewis.
Thank you. Right, so can people see my slides? There they are. Excellent, wonderful. Okay, so thank you very much for the invite. And is there a bigger question? Of course, I mean, philosophically, we have big questions, but this question about whether or not we are alone in the universe is one which, of course, we have wondered about over centuries. Now, is this the only planet in the entire universe where there is life, or at least intelligent life? Or is life out there and the universe is teeming with other beings, and one day we are going to join this sort of intergalactic sort of civilization that's out there? We're just waiting to get to the right level of technology, and we can be out there and we can join the rest of the universe. What I want to do tonight, though, is I want to take a bit of a scientific perspective with regards to this entire question of, are we alone? Now, I should point out that, of course, we only have one planet with life, and that's the one that we're on. And we only have one planet with intelligent life, and that's debatable. And a lot of what I'm going to be talking about is somewhat speculation rather than robust science. But I just thought I'd give you the sort of viewpoint from my perspective of where I think we are in this entire question of where we are with regards to other life in the universe and the question of, are we alone? So let me just see if I can advance my slides here. Oop. Give me 1 second. Here we go. There we go. So, of course, question one is, why should you listen to me? Who am I? Have I just walked in off the street to talk to you about this subject? So, as was mentioned in my introduction, I'm a professor of astrophysics. I'm based at the Sydney Institute for Astronomy, part of the University of Sydney. And I've been a research astronomer now for going on more than a quarter of a century. And my focus in my research has been cosmology. What I'm interested in is trying to understand the dark side of the universe, the dark matter and dark energy, which are basically shaping the universe that we see around us. And I do that through various topics, including this one known as gravitational lensing, where I use the fact that mass can distort the path of light through the universe to map out dark matter, and galactic cannibalism, whereby I can use the fact that big galaxies are eating smaller galaxies, in that they grow over time, and through that again try and work out how the universe has behaved over billions of years. I'm going to be shameless in my self-publicity here. I've written a few books on cosmology, and as was mentioned, my most recent one, Where Did the Universe Come From and Other Cosmic Questions, was just recently published. I touch on a lot of topics with regards to cosmology here. But in the book that I wrote several years ago, A Fortunate Universe, I was asking the question not only about life in our universe, but life across this potential multiverse of universes out there. So I've had a lot of in-depth looks at the meaning of life in terms of how could life form and how does life develop, etc. And I've used that to sort of guide me in the question of where are we with regards to life in our universe. So, of course, we have to start with, how do we think about aliens? And we're informed about life in the universe, I guess, a lot through fiction. At least I was when I was growing up. And we have to think to ourselves, what are we imagining is out there? And this picture here, of course, is H.G. Wells' famous War of the Worlds. And in this book, the Martians, our closest potential alien life out there, came to Earth as an aggressor to take over the planet. Their planet was dying, so they came here. And their goal was essentially to replace humankind and be the rulers of this planet. And of course, it's a common trope in science fiction that alien life is out there, and essentially they're out to get us. Okay, so if they discover that we're here, they're going to come and steal some of our resources, and whatever it is that it's probably best for us to be quiet and not let the rest of the universe know that we exist. But that's not the only trope that we have in science fiction with regards to aliens. Another classic book, and one I didn't actually read until I was an adult, was Arthur C. Clarke's Childhood's End. And in this book, there are aliens again, and they come to Earth, and they have a very different objective. They're not here to take over the planet, but they're here to help us, and help us in a strange kind of sense. They weren't here to help us individually, but help us evolve as a species. And so it was all about us going from being this planet-bound species on Earth to taking the next step in evolution, where we would become this species that is part of the overall galactic sort of civilization. Now, I didn't read Childhood's End until I was an adult, but one book I did read when I was a teenager, of course, is this classic, The Hitchhiker's Guide to the Galaxy. And this gives us, again, a very different portrayal of aliens, right? That in Douglas Adams' mind, that the galaxy was rich with different kinds of aliens, and they just didn't care about us, right? We were on this planet in this unremarkable part of the galaxy. And of course, the story is based around the fact that these aliens have decided to build a bypass. And to do that, the solar system effectively has to be demolished. The same way as that we might build a bypass around a town and demolish various bits and pieces. It's not important to us. But of course, there's another story. And this one, of course, is now appearing as a TV series on Apple, and this is Asimov's famous Foundation story. And in this book, there is life throughout the galaxy, but it's all human life. And what has happened in the overall story is that humans were effectively the only intelligent life in the galaxy, and they spread to occupy all of the stars, so there was a galactic-wide empire. And they even forgot the planet where they came from. So we've got this entire different viewpoint of what intelligent life out there could be doing. But of course, we think of aliens, and what we're thinking, of course, is we want to know, are there alien civilizations out there? Are there cities and creatures and scientists and all this kind of stuff? Is there entire sort of, I'm not even sure what the right word is, right? But you can imagine that we've got all these different planets with all these different beings, and they're all basically going through this growth of civilization. Some of them might be behind us, some of them might be ahead of us. But what we're hoping for is that out there is somebody that we could eventually talk to. And of course, in that talking, we could have hoped to learn a lot about each other, but of course, learn to advance our own civilizations by working out what each has discovered that the other is yet to find. So what does science think? What does science think about this possibility that out there are planets with civilizations, with creatures? They might be physically very dissimilar to us. They may even be mentally very dissimilar to us. But maybe they've got similar goals, right? Maybe their scientific goal is to understand the universe, and they've got their own kind of particle physicists and people working in gravity and all the kinds of things that are going on. What we need to do is take a look at what we know. And of course, yesterday was the Nobel Prize in Physics. And it was awarded for some really cool work that's been done, understanding what's going on, essentially at the small scale with regards to what's known as chaotic behavior, and also how that maps to the larger scale, which is chaotic behavior in our own atmosphere, and how that relates to the overall global warming effect that's going on. But a couple of years ago, these were the Nobel Prize winners in physics. So Jim Peebles, who is somebody I knew of when I was growing up, he is somebody who revolutionized our understanding of cosmology, how our universe has evolved and changed. And Jim Peebles did a lot of his work in the 1960s and 70s, and of course now he's retired. But on the other side, we have these two guys, Michael Mayor and Didier Queloz. And I hope you can tell by looking at Queloz is that he is not an old person. He is still rather youthful, because the discovery that these guys made was only really made in the last few decades. People have wondered about life in the universe for a long, long time, and people have realized that to have life, you needed sites for life, and the obvious place for those would be planets orbiting other stars. But the problem is finding planets around other stars is really hard work. And it wasn't until the late 90s and into the 21st century that people realized that they now had the technological power and telescopes large enough that they can hunt for planets. So this Nobel Prize was awarded for the discovery of an exoplanet orbiting a solar-type star. And that phrase is already tantalizing, right? A solar-type star, a star like the sun. And you already say to yourself, oh, what does that mean for the prospects of life? The evolution in this field over the last couple of decades has been exceedingly rapid. And we now have had space missions, and we have forthcoming space missions to hunt for planets around other stars and to work out what's the chemistry going on those planets. So we've had satellites like Kepler and TESS, etc. And to find a planet, once you've got the technology, and that's the important part, is relatively easy. What we've got in this picture here, we've got the satellite, but in the sort of graph that we've got time across the bottom, and we have the brightness of the star up the side. And what you can see is that the brightness of this star is remaining constant for a couple of days, and then drops down by only, some fraction of a percent, and comes back up again, and then drops down again, comes back up again, drops down again, comes back up again. And the interpretation of what we're seeing here as an astronomer is that quite clearly our star is just sitting there, and something is occulting the light. Something is going in front of that star and blocking out the light, so we see these dips. And this has become one of the most productive ways of finding planets, right? You look at stars, you measure their brightnesses very accurately, and you look for these dips, and that can tell you the size of the planet, and you can work out its orbit and all these kind of things. What happens is that people start to get very excited. Now, the first planets that we found were very unlike the Earth. They were very massive planets. They call them hot Jupiters, and they were orbiting very, very close to their stars. So they were basically bathed in this intense radiation, which would make life impossible. But as we gathered more and more data, we were able to look for planets which were closer in size to the Earth and in an orbit similar to the Earth's. And so we start to see this kind of news. So this is 2010, right? Only a decade ago. The first truly habitable planet discovered, experts say, right? So there's a planet, it's sitting at a certain distance from a star, and it could be habitable. But of course, what kind of happens is that the media gets excited and an astronomer says something that they later regret. And for this same discovery, an astronomer makes the statement, odds of life on newfound planet, Earth-sized planet, 100%. And that's just not true, because we don't know anything really about this planet. We don't know what its conditions are like. All we know is that it has an orbit around a star, and the orbit is a certain distance away, that it could potentially have liquid water on the surface. But we don't know if the planet has water on the surface, and we don't know if it has life. But this is an important thing, right? As I mentioned, people have wondered about this question of life in the universe for a long time. And many of you have heard of this particular equation known as the Drake equation. For most of the last century, this equation, which we'll go through in a moment, it contains it contains terms in it that allow us to try and estimate how many sort of advanced civilizations we expect to see in our galaxy. And most of those terms are things that we don't know. But what has happened over the last few years is that with the discoveries from telescopes such as Kepler, we are starting to get a handle on just how many planets are out there. So we still need to take a look at this estimation from Frank Drake, and he first wrote down this equation back in the 1960s to see what the prediction is for there being civilizations out there in the galaxy that we could potentially contact. So we'll just go through the equation, right? Basically, it multiplies together a whole bunch of terms. And at the end of this, what you get is an estimate of how many civilizations there are. And the first term that goes into that expression is the average rate of star formation every year in our galaxy. And again, I'll come back to this. This is something that we actually know quite well. Then we have the question of the fraction of stars that have planets. Now, from Kepler, we now know this, right? In terms of, we've looked at a certain number of stars, we've looked at how many have signatures of planets. We can now work out what the fraction of stars that have planets is. And we know that this number is essentially almost 1. Every star system we look at has signatures of planets. Then we start to hit some more interesting terms. What's the average number of planets around a star that can support life? Well, if we take our solar system, we know that this number is 1, but we have a sample of 1. So we don't know, are we the extreme one way, i.e., most planets have none and we're the extreme that we have 1? Or we're the extreme the other way, that we have 1 and other systems could have 10 or 15 planets that could support life. Then we have the fraction of those planets that could develop life. Now, of course, we don't even know what the conditions were on Earth for life to develop. So we've got to try and extrapolate, use our knowledge, and there's an entire field of astrobiology, which is trying to come up with this number of, how prevalent is life in the universe? What fraction of planets, what planets have the conditions where life could form? Then things get even trickier. What fraction of planets actually go on to develop intelligent life? This is a question that essentially we've barely touched on. A few people think about this, and we'll come back to this later on, the entire question of intelligent life on a planet is not a simple one to answer. Then we get to the fraction that can announce their existence by sending out signals into space. Modern humans have been on this planet for hundreds of thousands of years, and it's only been in the last 100 years that we've been able to announce to the universe that we are here, right, through radio waves being sent into space. So, again, what is this fraction of beings out there that could be announcing themselves? And then we have to build in a very important factor, the longevity of the civilization. And this is one that people don't like to think about. How long does a civilization last? And, we can look at great civilizations on Earth, such as the Romans and the Greeks and the Persians. And there are various time scales involved, but, empires rarely last for 1,000 years. Technological empires, well, at the moment, we don't know. We're only 200 years or 300 years into modern science, and we don't know how long our civilization is going to last in terms of being able to communicate with the rest of the universe. But if we know all of these factors, we can multiply them together, and that should tell us how many civilizations are out there that we might be able to communicate with. So just as a reminder, right, we've got this entire sequence of numbers that we want to multiply together, and some we think we know, and others are a little bit, more hand-wavy. So for the Drake equation, the things that we do know, we robustly know how many stars there are in the Milky Way galaxy. There's roughly 200 billion stars. And we do know that there are roughly 2 stars born every year. Now, again, 2 stars born every year doesn't sound like a lot, but the lifetime of galaxies are billions of years. So, this is a lot of stars that are being born over what is a cosmological timescale. And as I mentioned, we also now know that there's lots of planets out there. And I do love this little graphic. This is known as the Kepler orrery. And this is a representation of, and this is a couple of years old now, I think. This is a representation of the kinds of planetary systems that are known out there. So we've got various kinds of stars. Some have 1 planet, some have 2. We now know of planets that have, we now know of stars that have multiple planets orbiting them, some close in, some far out, some possibly resembling the solar system. Most of them are quite different. So these are the things that we know quite well. But most other things, they're a bit of a guesswork. So we have to estimate these other terms, right? Fractions of planets that could host life, life that turns into intelligent life that communicates, longevity of a civilization. And if you look at the literature on the Drake equation, right, what you find is that there's no single answer. As you'd expect, right, science doesn't have a single number that comes out of the Drake equation. What we have is numbers reflecting what people have as inputs. And what we get is that the estimates to the number of civilizations that are out there in the Milky Way are numbers between 10 to the minus 10. So this is 0.009 noughts and a 1 to 10 to the 7, which is 10 million. So this immense range, of course, has profound implications for what we think is the potential for life in our Milky Way galaxy. If it's the 10 to the 7 side, right? So we're saying that there are 10 million advanced, intelligent, communicating civilizations out there. It does mean that aliens are everywhere, right? Our galaxy is big, but if you chop it into chunks, right, into 10 million chunks, there's quite a lot of those. So there'd be an awful lot of alien life scattered through our galaxy. But on the flip side, if it's 10 to the minus 10, then we are alone. We're effectively a fluke, and we might be a transient fluke. There might be another transient fluke at some point in the future, billions of years ahead, or even billions of years behind us. But if it's 10 to the minus 10, then we are alone. I think, most people sort of say, right, let's, split the difference. Let's go somewhere in between. Let's say there's 10, okay? So let's say that they're out there now in our galaxy. We'll be quite conservative with our numbers, that there are 10 civilizations that we could potentially have communication with. So we have to think to ourselves, well, what would the consequence be if it was 10, right? Is it this number 10 and they are civilizations like us? So maybe they're scanning the skies looking for radio waves and looking for, neighbors from some other civilization. But we have to think a little bit more deeply about what this number actually means. The issue is that our Milky Way galaxy, right, our home, is roughly 10 billion years old. Now, it's very hard to define the moment that a galaxy is born, because a galaxy is one of those things that continues to grow over its life. But we know that it has been a sizable mass for roughly 10 billion years. Now, halfway through its life to date, roughly 5 billion years ago, the sun formed, and soon after the Earth formed. And in that 4.5 billion years, the Earth cooled and life has evolved, and you find us here sitting today on the Earth. And of course, we feel that we're a pretty technologically advanced civilization. Now, the thing that makes this situation kind of interesting is that, as I said, our galaxy is 10 billion years old, and it's been creating stars like the sun over its entire lifespan. So what we've got is that maybe 7 billion years ago, a star like the sun was born, and the material settled down and formed a planet. And there's a planet that is something like the Earth, and it has a 4 billion year head start on us. So for us, right, 4 billion years ago, the inhabitants of this planet were at where we are today. Then the question is, what happened in the next 4 billion years, right? Even if this happened 10 times over the life of the Milky Way galaxy, and we expected to get these planets where life formed, we have to remember that the timescales that we're talking about are immense. So we're not talking hundreds of thousands of years or millions of years. We're talking about planets that could have billions of years on us in terms of time. And so we have to wonder, what could a civilization do in that time span? Now, one of the ways we like to understand this is something that's known as the Kardashev scale. And Kardashev, who was a Russian astronomer, he only died either this year or last year. He proposed this scale a while ago, and it's a way to sort of classify what stage an alien civilization might be in. So he had a type 1 civilization, and that is a civilization which basically utilizes all of the energy provided by its star that falls onto its surface. So in terms of human civilization, right, what we're talking about there for the Earth, that's around 10 to the 16 watts. Now, we are not a type 1 Kardashev civilization yet, but we're getting close. But of course, we're getting close by essentially getting energy from fossil fuels rather than gathering sunlight. But, you know, as things go on and we run out of fossil fuels, they're not going to last for thousands or millions of years. Then what we're going to have is that we're going to turn to this question of using sunlight to power our planet. Of course, once you start with that situation, you realize is that as well as the sunlight you can gather on the surface of the Earth, there's an awful lot of sunlight you lose, which just goes off into space. So Kardashev designated a type 2 civilization. So a type 2 civilization is a civilization that harnesses all of the light produced by its local star. So if you could imagine, what we're talking about here is that the Earth has gotten to the point where we or our descendants or whatever have developed a technology where effectively we can wrap the entire sun at the radius of the Earth with solar panels, so we can collect all of that energy. So that means that we go up in energy by a factor of around 10 to the 10. So once we harness that much energy, we can do an awful lot of things. We can use energy to run computers and build spaceships and travel to other stars. Of course, if we get to that stage where we can travel between the stars, when we get to the next star system, obviously what we want to do is harness the energy of that star that we arrived at. And Kardashev designated a type 3 civilization as one in which is using up all of the energy produced by stars in that galaxy to power the civilization. Now, what we've got to think about is what's the time scale involved here to go from a type 1 civilization to a type 2 civilization to a type 3 civilization? Is it millions of years? Is it billions of years? Where do civilizations stand in this kind of picture? In this little movie here, I'm just going to sort of point out something that probably people don't realize. This is a little project that was set for students in the US. It was an international school, and it was the question of if you start at one star in the galaxy and you head off and you go exploring and you come up with different strategies on what you're going to do, right? So you're going to fly from this star to that star and then set up a civilization, and then from that star to the next star. How long would it take you to colonize the entire galaxy? Now, the galaxy is big, right? We know the distance between us and the next star is roughly 4 light years. And we know that the Milky Way galaxy is roughly 100,000 light years from side to side. And we know that in general, spaceships can't travel at really high speed. Let me just go back and run that again. I do like this little movie. Okay, so we have spaceships that travel often at sublight speed. So we could talk about thousands of years between the stars. Well, it turns out that the time scale to colonize the entire galaxy is of order between 1 million for the fastest ships to 10 million years. Now, to humans, 10 million years is an awfully long time, right? That's sort of the time scale of which we've been evolving from chimpanzees on this planet. So for us, that is an immense amount of time. But in terms of the Milky Way galaxy, 10 million years is the blink of an eye. It takes the sun 250 million years to complete one orbit. So in a fraction of the orbit of the galaxy, if you had a civilization on Earth that could, essentially equip itself to travel over interstellar distances, in 10 million years, we could entirely colonize the galaxy. But remember, we've been talking about civilizations that might have billions of years on us, not millions of years. So that already opens up a few interesting questions. If they're out there and they're doing this, okay? So if these creatures are out there and they are flying to stars and they're, arriving and they're setting up their civilization, as I mentioned, they're going to potentially set up a system whereby they're going to harness the starlight. And this is this idea, this isn't the first idea this was proposed, but it was made famous by Freeman Dyson, and it's known as a Dyson sphere. But if you know your science fiction, it was Olaf Stapleton in Star Maker, I believe the book was, that proposed this, that civilizations might essentially wrap their stars in structures to harness light and therefore run their civilizations. So if we had a civilization in the galaxy that was flying around between the stars, maybe taking 10,000 years to get between the stars, they get there, they build these immense structures and then fly on to the next star. The issue that we have as scientists is that any life out there that's doing this would be absolutely and utterly obvious. The notion of a Dyson sphere, in terms of physics, is quite simple, right? What you're doing is you've got a star at the center, it's radiating starlight, which is optical light, and it's falling on your Dyson sphere. So what we've got is this picture that starlight comes out, and your Dyson sphere is effectively giant solar panels. And that solar panel that absorbs the radiation, and you take that radiation and you do something with it. You run computers, or you generate fuel, or you just run the lights or boil the kettle or whatever you do. But we have a rule in physics, okay? We have the second law of thermodynamics. And that second law of thermodynamics says that if you're going to use energy, then you're going to degrade the energy. And it goes from being nice high energy optical light, and it becomes wasteful energy, which is infrared radiation. So if we've got these Dyson spheres out there, then they should be replacing the starlight, which is optical and which we can see, with infrared, which we can also detect with our telescopes, right? And people have searched for this. They've basically scoured the sky looking for the signature of Dyson spheres. And if you could imagine that in our Milky Way, if we had a civilization spreading through, we might expect that a chunk of our galaxy, in terms of starlight, would have disappeared and would have been replaced by infrared emission. And the result is, so far, is that there's no signature. We don't see any sign that there are these Dyson spheres out there. So it doesn't look like we've got a civilization which is spreading through the galaxy and using starlight to power its civilization. There have been some intriguing things out there. Astronomers get drawn to things that just don't behave the way we expected. And some of you may have seen this in the news for the last few years. This is a thing called Tabby star. And again, this was a star that was looked at by Kepler. And in this picture, we've got the light curve. So time along the bottom, brightness up the side. And you can see this star is relatively constant, but every so often there's a bit of a dip. Something's going around the star. But at some point, there was this crazy up and down motion, which is highlighted in the bottom there. And what we've got are big chunks of starlight being occulted by something. Now, of course, right, most science thinks that this star is surrounded by chunks of ice and gas and dust. It's a young star, and it's just a very messy environment, and that's what's giving us this really sort of crazy signature that we see. But of course, what the press wants to hear is that what we're seeing here is a Dyson sphere falling apart. So this is an artist's interpretation of a Dyson sphere it's an aged civilization. The Dyson sphere hasn't been maintained. It's fallen apart. And these chunks and bumps that we see in the light curve are all these broken bits of Dyson sphere that are floating away. It's good to sell newspapers, but of course, science is more than just the headline. And I said most people think that it's just a rather messy environment. So we don't see them. And this is something that has bothered me for a long time. When people talk about looking for aliens, it's all about peering at stars and listening very carefully. Can we hear their radio signals, etc.? And in my opinion, if there are civilizations that are out there that have billions of years on us, then they should be obvious. We should be able to see them. Their signature would be like a flashing Coca-Cola sign in the sky. So we have to ask the question why we don't see them. And then we run into an entire mountain of literature, okay? People have written more papers on why we don't see something than, what we do really see. This, of course, is related to this person. This is Enrico Fermi. He's a famous particle physicist and, was very active in the very early years of nuclear physics. He was involved in the first nuclear reactor, etc. But there's a story that in the 1950s, he was having lunch with a bunch of scientists, and they were talking about aliens. Of course, 1950s, UFO craze. And Fermi asked the question, and he was not the first, but he asked the question, where are they? Because he came to a similar conclusion, right? Aliens out there, alien civilizations should have a big head start on us, and they should be obvious. So the question is, are they too advanced, right? Are we not seeing them in the same way as, an ant might not recognize us? Are they too advanced? And maybe they are, but what we have to remember is that starlight is the cheapest energy in the galaxy, right? There's stars everywhere. You can go and harness their starlight. You might come up with new technologies to, harvest dark energy or something, but who's going to not try and harvest the cheapest energy that they can have, right? And, given an Australian energy company, we would bundle it up and sell it to somebody rather expensively. So there's lots of stars there. So even if they're advanced, it doesn't answer the question of why we still see all the stars out there. Maybe they are too alien. Well, what does that really mean, that they are too alien? That they don't require energy to drive their civilizations? I mean, they might be alien. We might not understand their music and their television or whatever it is that they do. But, the laws of physics are rather universal, and we do know that to operate thought, energy has to flow. And it would be very interesting if they've got a way around that aspect of the universe. So they might be alien, but they, to quote Star Trek, they cannot break the laws of physics. Maybe that they're not interested in travel. Well, this is another interesting one. This is almost they are too alien. And it's a weird one, isn't it? Because if we think about us on Earth and all the different kinds of people that there are clearly many people that want to stay at home. But in that mix of people, there are always the one or two adventurers that want to get out there and do something. And we're not talking about one civilization here. We could be talking about multiple civilizations. Are we saying that all these civilizations are not interested in travel? That would make humans very, very weird, because one of the key things we have done over our time on Earth is travel the planet. Maybe everyone is listening. Maybe everybody is too scared to announce that they're there. Well, what are they scared of? Right? We're looking at the sky. We're not seeing signs of anything. For us, the universe out there looks like a big, empty, ocean ready to explore. There's nothing frightening out there. There's no reason to be quiet. But maybe it is that we haven't just worked out the lay of the land yet. But even if there was something to be scared of, that something to be scared of should be obvious. Maybe they are too far away in space. This is one that's been put forward. Again, I don't buy this, right? Far away in space means long away in time, but those kind of time scales and distance scales, given the distances in the universe, they're not large on the time scale that it takes for the galaxy to do anything. And again, they're not large on the billions of years that a planet has had, that the civilization could have been advancing before we even came down from the trees. We're in a zoo, right? This is the zoo hypothesis. This is a very weird one in my mind, that we are being kept as some sort of exhibit. Look at these creatures, right? These are these primeval little things that haven't even worked out how to travel between the stars yet. But the thing that gets me about the zoo hypothesis is that if you ever go to the zoo and you're looking at an animal in the zoo and you're there watching very carefully to try and understand how the panda behaves, etc., not far away there will be a kid with a rock or a stick to throw at the animals to find out how they respond. If we're in a zoo, it's a zoo with very good rules to stop us being bothered with, right? Again, this is a similar one. Maybe they are waiting for us to grow up. But again, why should they care about waiting for us to grow up? Where do we stand in this entire sort of galactic civilization thing? It's a strange one, is that you could imagine that there's a civilization out there and they've all agreed that they're going to wait for us to become a civilization of a certain level, and yet there's not going to be the one or two malcontents that think, oh, we'll go and poke the bear and see what happens. And of course, the one that of course the Skeptics Society knows about is that maybe they're already here. And if they are already here, then what I want to know is how they don't show themselves to astronomers who spend all their time outside and always seem to find Americans on back roads and freak them out with their light shows. So this question, I think, is an important one, and I don't think that it's answered, right? If they're out there, they should be obvious. This is an example of a paper that was published only a couple of years ago, and this was put forward by a couple of people that said that essentially civilizations use up so much energy that they get to a point where effectively they put themselves to sleep until the only energy that's left in the universe is the energy that's left over from the Big Bang in the cosmic microwave background. And they're all asleep and they're all waiting to be reborn. But again, remember, these things are happening, if they are going to happen, over the lifetime of our galaxy at different times, and we're going to expect to see civilizations in different states. And we can't expect that they all have already reached the state of being asleep, waiting for the future universe. We should expect to see them out there now. This one, again, is another interesting one. People have wondered if civilizations out there are technologically advanced. And this is one that I've been thinking about recently is, why did we go past the agricultural revolution? What was the tipping point that took us past the agricultural revolution into the technological revolution? And it's not clear to me what the actual steps were. And what I mean by that is that I don't see that the technological and scientific revolution were guaranteed by the fact that we had an agricultural revolution. And some of the books I've been reading recently have suggested that, it could have been as easy for us to give up agriculture again and give up the notion of technology and go back to being hunter-gatherer populations. But maybe this is the way out. Maybe we suddenly found ourselves along a path where we are technologically advanced and other civilizations just didn't get there. The key point, I think, in my mind is this picture. Now, hopefully there's some sci-fi fans watching here and you recognize various aliens. And of course, these are all aliens from the minds of humans, which is why many of them look like humans, right? But the important point is that these are aliens that have been imagined in terms of our science fiction. And we have aliens who are sort of in terms of Mr. Spock. We have aliens who are really destructive in terms of the Daleks. We have aliens who want to come and hunt us in terms of... We have Alf, who is just a comedic creature. But we've got all of these different kinds of personalities and drives and goals and focus sort of ideas. And we have to imagine that different civilizations will have similarly different goals and drives and all this kind of stuff. And if you're going to propose a single solution to the Fermi Paradox, then you explain to me why all of these different potential beings and almost the infinite number of potential beings that we haven't imagined would have the same goal at the end of the day. Maybe some do stay at home, will travel. Maybe some do go to sleep to wait for the end of time, but others will do something different. So in my mind is that if we have technological civilizations in our galaxy, they should be out there and they should be obvious. Oh, now I realize, sorry, I'm speaking for far too long again, so it's already coming up to 8 o'clock. I will try and speed up slightly. So we still have this question of where are they? And to me, the obvious answer is that maybe we're alone. Maybe that's clearly the thing that's going to be a solution to all these problems. So let's try and understand quickly why we might be alone. And of course, what we're talking about is where can we have life in the universe? And one thing you probably know about is this notion of a habitable zone. And this, as I mentioned previously, this is the distance from a star where maybe where you can have liquid water. So for our sun, Venus is too close to the sun, essentially it's too hot to have water. Earth is more or less just right. Mars is at the outer edge of the habitable zone. And all these different stars have different habitable zones, and they're at different radii based upon how much energy is being put out by the star. But what's less known is that galaxies have habitable zones. So this is a representation of our Milky Way galaxy. And we're in the green region, but the outer part of the galaxy, what we now know is the outer part is sort of chemically poor. There's not the rich mix of chemicals we need for planets and lives, etc., because stars just haven't had enough time to go through lots of generations to produce the materials that are needed. The inner part of the galaxy, it's quite different. There, everything's just too active. There's just so much going on. There are exploding stars, etc., that it's very difficult to have life in that central part. So even though there are 200 billion stars in the Milky Way galaxy, we already rule out a large number of them from the fact that they are in the wrong location. As well as that, even in the habitable zone, we have really violent events. So the two key ones are supernova and gamma ray bursts. So these are immense stars that go through their lives, and they get to the end of their lives and they explode. And in those explosions, they throw out huge amounts of energy and radiation, and that energy and radiation can sterilize planets within a certain volume. Supernova are relatively local, but gamma ray bursts, which are intense versions of these exploding stars, could sterilize up to a third of our galaxy. Also, we know that in the middle of our Milky Way galaxy, we have a supermassive black hole. It's roughly 4 million times the mass of our sun, and every so often it eats matter. And when it eats matter, it gets really hot and shines, and that radiation that's given off can be very dangerous for planets in our galaxy. And some of you, again, who might read classic science fiction, there was a really nice book by Fred Hoyle, who was an astronomer from the last century, called Inferno, where he had this idea of the center of the Milky Way galaxy consuming matter and lighting up, and essentially made the southern hemisphere of the Earth and inhabitable because that's the side that faces the center of the galaxy. And everybody on Earth had to move to the northern hemisphere, and our heroes basically tried to hide out in northern Scotland. But it's a real thing, and these supermassive black holes, they go through these periods of rapid feed-in, and then they're quiet, and then rapid feed-in. So there could be these bouts of essentially sterilization events that occur over the lifetime of a galaxy. The other thing that we know is that most star systems are not single stars like the sun. And so we know that we have binary star systems. And in a binary star system, strange things can happen to the planets. So here we've got two stars, and they're located at the sort of bright points you can see at either side. And the gold line, that is the orbit of a planet. And you can see what happens is that the planet basically gets passed back and forth between the stars. What that would mean is that sometimes the planet is near the star, so it's getting lots of radiation. Other times it's far away, so it's getting frozen. And we think that one of the reasons that we have life on Earth is that it's had a relatively stable climate for a long period of time. In this kind of star system, these planets would freeze and thaw and freeze and thaw and freeze and thaw over many, many different time scales. And we just do not know what the prospect for life would be. It gets worse because actually a number of stars are in multiple systems. So you can have planets orbiting 3 stars rather than 2. And if you want to know more about that, then there was a science fiction book a few years ago, The Three-Body Problem by Cixin Liu, which basically uses this notion. And again, what happens is the orbits of planets can spend a long time out far away from the stars and coming close and get thrown back out and coming close, etc. So many stars are ruled out because they're in multiple systems, but even stars based on star types are ruled out. Our sun is a G-type star, so it's down there towards the left-hand side. More massive stars, they're not really good places for life. Right? They live less than 1 billion years. Now, it took 4 billion years for complex to arrive on Earth. So a star that lives less than 1 billion years, and some of these stars live only 10 million years, are not good places for life in terms of timescales. Also, they produce a massive amount of ultraviolet radiation, and that can rip molecules apart. So we don't think these hot stars are good places for life. The cool stars, which are the most numerous stars in the galaxy, they're known as red dwarfs. They are much more feeble than the sun, but they live a long time. But they're also cantankerous. So they tend to be very flary. And what I mean by that, we know what solar storms are on the Earth. We get hit by these solar storms every so often. They disrupt communication satellites, etc. But it looks like these red dwarf stars are pumping out lots of energy in these constant bursts, basically solar flares. And people are coming to the conclusion that a planet that needs to be close enough to a red dwarf star to be in the habitable zone is probably going to be too close because it's going to be hit by all of these solar flares. Another problem you have is that planets, when they get close to their star, they get locked in their orbits. So it's thought that planets orbiting red dwarfs are these things known as eyeball planets. What that means is they essentially keep the same face pointing towards the star all the time, in the same way as the moon keeps the same face pointing towards the Earth. In the best case scenario is the picture we've got on the right here, where one half of the planet is frozen solid, the other half is absolutely arid desert, and around the edge of the planet in the twilight zone, there might be the problem with water and life. But as you can probably imagine, thinking about life evolving in this complex, in this sort of complex environment is going to be tricky to do. So we effectively rule out most of the kinds of stars and star systems in the galaxy for hosting life. The other weird thing is that when you think about the amount of water that a planet has, the Earth is kind of weird, right? 70% of our surface is covered in water, 30% is land. And when we think about planets and people scribble down the numbers, it turns out they think that planets should either be desert worlds, completely devoid of water, or water worlds, 100% covered in water, right? Those are the two kinds of norms. And to get something in between is something which is somewhat extreme. So the Earth looks like, even though it's around one of the good stars, we seem to be on a bit of a weird planet in that we have some land and some water, unlike most planets that we'd expect to be out there. And this is important because the entire picture of where life comes from appears to require not only water, but tides. Now, I spoke to some people who work on what they think were the first steps in the formation of life. And they said the critical stage is for the chemicals get wet and then dry and get wet and dry and get wet and dry. And clearly you can't do that on a world which is completely covered in water, and you need tidal regions where water comes in and washes out. So this has led to this entire notion that our Earth is potentially a rare planet, right? So this book, which I read a long time ago, I still think is kind of cool, Why Complex Life is Uncommon in the Universe, points out that there are lots of weird things about the Earth, right? The fact that our sun has been stable for billions of years, that many stars are much more variable, some are very flary, some of their temperatures go up and down on very short time scales. We've got a very stable star. Of course, we're in the habitable zone, right, where we should expect to find ourselves. We're also in a circular orbit around our star, right? So our climate doesn't vary much during our year. If we're in a more elliptical orbit, we'd have more extreme weather events and we don't and climate events, and we don't really understand how that would affect life on Earth. We live in this sort of wet/dry world. We have a molten core with a magnetic field which protects us from the sun. I mean, Venus has lost its magnetic field, Mars has lost its magnetic field, which means it gets impacted by the solar wind. The Earth has a magnetic field which appears to protect us, and other things which we think contribute to life on Earth. So again, maybe what's happened is that we are the exception, right? We've stood out that that life in the universe, that we drew the lucky straw and we are here, but most of the universe is potentially dead and sterile, or at least not hosting intelligent life. Let me do a quick time check. I'm slightly over time. Am I allowed another 5 minutes? I don't hear an objection, so I will continue. So another question, of course, is intelligent life inevitable? And, you know, when I was a kid, you'd pick up your Life on Earth book and you'd open this. And of course, you know, love these kind of pictures. But what I didn't realize, of course, is that I couldn't read a non-linear time scale. And it looks like, you know, that you have the mammals and dinosaurs and humans. And this is all of human history packed into what appears to be a relatively short time scale. And again, it gives you this idea that there's this march of progress. You go from the very basic Earth on the left to us intelligent humans on the right. But it's an eye-opener when we look at the actual timescales that are involved. Okay, so this is the version of Life on Earth that I like. Modern humans have been around for roughly 2 million years. The red bar you can see there are the non-avian dinosaurs, right? So that's your Stegosaurus, your Triceratops, and your T-Rex. And then we've got the other animals that have been on Earth. When we zoom out and look at the entire history of the Earth, what we realize is that, you know, there was a small chunk of the Earth's history where there was no life. And then the vast majority of the time on Earth, life has been single-celled organisms, right? Very, very simple life. And then roughly 500 million years ago or so, more complex life arose. And we don't know why, after billions of years of single-cell organisms, life decided that complex is the way to go. And we arrive today, and we still do not know why humans are intelligent, right? Why we've got to this stage of worrying about and thinking about the universe. We don't understand why us now and not the dinosaurs, right? Why didn't the dinosaurs develop intelligence? It was one of those things that was like predestined. That's where evolution is going. They were around for more than 100 or so million years. So maybe even if life is out there, intelligence is rare. Now, there's been suggestions about maybe intelligence does arise, but of course what it does is it snuffs itself out very quickly. And of course what we realized is that intelligence has risen in humans over the last 15, 20, 100,000 years. And suddenly we find ourselves being able to send signals out into space. And at the same time, we've been able to do this. And of course, this is a hydrogen bomb explosion. And this is from the 1950s. And we've arrived at this point where our technology is a double-edged sword. It is, of course, the thing that allows us to understand more and explore the universe and all this kind of stuff. But it is also the thing that has given us the ability to destroy ourselves. And it's not just through nuclear weapons, but climate degradation and all of the other things. And I think we all know that civilization, in terms of the entire picture of us being able to communicate with the rest of the universe, to keep going out into space, has balanced on a knife edge, right? It just takes one decision on Earth, and then, as the phrase goes, we could be bombed back to the Stone Age. So maybe it's not just us that face this kind of dilemma. Maybe every civilization does. Maybe intelligent life does arise. And we've got to ask then about this notion, which is known as the Great Filter. Does every intelligent species basically wipe itself out? And there's some options. Maybe we haven't yet reached our Great Filter. So maybe there is life out there evolving in the universe, and we just happen to be lucky. Maybe something couldn't happen for the first few billion years, and we're amongst the front runners. And out there maybe are a few civilizations which are similar to us. We haven't heard about each other yet, but we're all facing this Great Filter. But the filter might not be there. Maybe we would all become type 3 civilizations in the future. But maybe we're lucky, right? Maybe we're lucky in the sense that we have been through the filter, and we don't really know what that was. That whatever it was, it might have been something in our minds that allowed us to do scientific problems or whatever, that we've been able to get past a point where civilizations have been continuing to advance. We didn't go back to hunter and gathering kind of societies. We decided to push on. But for everybody else, that was a filter that left them behind. So maybe what we've got is that maybe there are some more things ahead of us, but we might still get to that type 3 civilization. Or maybe the Great Filter is an absolute. Maybe civilizations do wipe themselves out before they get the chance to fill up a galaxy with a galactic-wide civilization. And maybe this is something that is still in front of us, in that we are talking now about climate change. Again, we're back talking about nuclear weapons. I'm so glad when the 90s arrived and I thought we didn't have to do that again. But maybe this is us, facing our future. So the Great Filter might be ahead of us. And of course, that means that we're likely to be filtered if we're not very careful. So maybe there is life, or there has been life, and there has been intelligent life out there. But it seems to me that we can be pretty confident that intelligent life has now gotten to the stage of being able to colonize a galaxy. maybe what's awaiting us if we ever get out there and explore it are the remnants of dead civilizations that basically got to a particular point and didn't continue. So I'll quickly put up my conclusions. Sorry, I do talk far too much. The universe is a tough place. Life could be rare. Even if life arises, it might never get past being basic slime, the single cell organism stage. Even if it does, it may never progress to intelligence. Even if it does, it might still face a great filter, and that might be ahead of us. But in my opinion, all this points to us actually just being currently truly alone in the universe. And I should probably stop there, and I'm happy to take some questions. Thank you.
Wow, what a fascinating talk that was. But I have very good news for you. I'm sure you'll be pleased to hear that we will know very soon now what's going on, because Captain Kirk himself is being shot up into space, I think, next week. All our answers are coming soon.
Yes, I'm not sure how a 90-year-old does with 4G, tell you the truth, but we'll see how that one goes.
It's Captain Kirk. It's going to be tremendous.
Yes.
He's going to. We're looking forward to that. Yes, lots of questions coming in. I only get time to get to a few, but that's all right. One of the things I'll just comment on is one of the reasons civilizations may perish, which is akin to what you were saying anyway, with adverse environmental goings on, would be an asteroid impact, and they weren't reached a state of advanced technology enough to combat an asteroid, so they could see it coming, and that's it, lights out. If the dinosaurs were aware, then that's what they would have said at the same time too. So there are many reasons. I can follow your reasoning. Mm-hmm. So let's get to some of these questions here. Okay, and here's an interesting one. Given that the nearest planet is several light years away, 4 you were saying, that would be Proxima Centauri, that's about 4 light years away, how could we ever communicate with intelligent life if we ever find it? So we've got the problem of sending out messages at the speed of light and waiting for answers at the speed of light.
Well, yes, that is an interesting one. I mean, it's a waiting game at some level. Of course, one of the problems that we have is that our human brains have a certain clock speed, right? And so, for us, a day is a relatively long time, but that doesn't mean that that's the clock speed of all life that's out of there. That 4-year period for us might not be a long period for, effectively life in the slow lane. Yeah. And I've been involved in discussions about life in future universes where there's less energy available, and whether or not life just slows down and that time travel speed sort of becomes irrelevant in the end. But it is something we would just have to live with, is that we would have to be able to send out a message and then just wait for a reply. But, it wasn't that long ago where people came to Australia and would send a letter to somebody back in Britain, and they would get a response in 6 months, right? Yeah,
you're absolutely right. And I think we do well, but we are somewhat limited, of course, by the state of our imagination and our ability to comprehend what might be possible. And in 20, 30, 40 years, that might dramatically increase. We can't know what our descendants will know, in other words.
Yeah, and look, there are some get out of jail free cards with Einstein's general theory of relativity that allow you to basically send messages faster than light by using things like wormholes. We just don't know if we could ever have that as a feasible technology. But there are ways around it. But if that doesn't come to pass, then yeah, there will be a bit of a waiting game that we have to play.
Yeah, but we can just use subspace like Star Trek. I mean, that'll fix it.
Yeah. But surely, if we're going to get information from a civilization that was billions of years ahead of us, we'd be having to wait a few years to get that, wouldn't we?
Oh, yeah, I think so. And of course, there's also the possibility that we're being bombarded with this all the time, but we simply don't have the technology to detect it.
Yeah, well, there is that, but then you'd have to ask yourself exactly how are they transmitting it and why in that particular method, right? So there's an entire thing around communications efficiency that you'd need to think about. But yeah, exactly. That's why people keep looking.
Yeah. Here's another question coming in. How diverse is the chemistry that could support life? For example, how important is water? And another sort of question I will take on to that is, how are we defining life? We can only define it by what we know on this planet.
Okay, so there's a couple of things that we know, right? So in terms of the elements that are available in the universe, we know that the most common element is hydrogen, followed by helium, and then we have carbon and oxygen. They are the most common elements in the universe. Now, it turns out, of course, that that means that the universe is actually very rich with water. Water is everywhere. And by everywhere, I mean, it's like all locations of the galaxy. It might not be on every single object, but there's a lot of water out there. There's also a lot of carbon available, and carbon is a very versatile atom. In fact, we have an entire branch of chemistry. Organic chemistry is based upon all of the fun things you can do with carbon. So given that, they are the building blocks which are available, and it shouldn't be surprising that that's what we are built from. So unless you're in a place in the universe where suddenly these things are rare, and it would be very hard to make them rare because they are the byproducts of the Big Bang and stars, then there are alternatives, but you would use what's the easiest thing to hand. Now, the definition of life is a lot trickier because life is one of those things that when you think you've defined it, you always find an exception which destroys your definition. And one of the definitions, well, there's a coupled definition that I like. Number one, that you need complexity. So you need to be able to process information, and you can only do that when you have a complex arrangement of atoms. So crystals, which are simple, can't store information, but DNA, which is made of the same bits, but you can put it in different orders, you can store information. So complexity. The other is the flow of energy. So you need to have, in physics talk, we talk about an energy gradient. So for us here on Earth, the ultimate source of life is the energy that comes from the sun. And all life is driven by reprocessing that energy. So plants do it first, and then animals eat the plants, and we eat the animals. And that then gets radiated back out into space as infrared radiation. So it's information processing, energy gradients are the two key things in my mind for life. But it's not an mission.
Yeah, I agree. It is tricky. And again, we're sort of hamstrung somewhat to what we know on this planet. And but you make a very good point about the basic building blocks you would need. Now, folks, there are a couple more questions, but I think we'll sneak in one more here. Somebody has put in this question: could many active intelligent civilizations have turned inward digitally, like inside a virtual space, given the challenges of interstellar travel? And I suppose that also comes into the question somebody also asked a little while ago is, do you think we're living in a simulation?
Yeah, no, that's a really interesting one. And again, another one that I've been reading up on a lot of the last few years. Biological life is horribly inefficient, right? I mean, I need, and you need, 100 or so watts just to tick over, okay? And when you calculate the amount of information that you process and think about what the limit is on information processing, you can do exactly the same processing with just a tiny amount of energy. So, biologically, the fact that I need this machinery for my thoughts is inefficient. And there is this big question of, can I translate that onto a computer? And so there are a number of people have been calculating how much life could be accommodated on a computer and running away with that. So instead of building a Dyson sphere to support life, you build a Dyson sphere to support huge computers where you don't have billions of peoples, but you have trillions of people, right? So you can pack that in. It is possible, right? I am not 100% adverse to the simulation argument that that's where we find ourselves, other than the fact that, in my mind, if I wanted to simulate the universe, I would have made it slightly different to the one I find myself in, right? I mean, you can think about how the universe could be better. I'm not adverse to it, but it doesn't sit well with me at the moment. But I can imagine in the future, if we can crack that, can you have electronic consciousness?
Yeah.
And we just don't know. We just don't know.
Maybe we're part of the mice experiment from the Hitchhiker's Guide after all. Well, listen, what a fascinating evening it's been, folks. I'm sure you'll agree with me. And I'd like to thank our guest tonight for sparing some time and discussing the wonders of the universe. And just to remind you once again that the attitude from Australian skeptics is that there's nothing that we would say that along the lines is there can't be any aliens, we don't believe in it, bah humbug. Of course, we're open to it, but what we do is we look for the evidence. Are they in fact visiting Earth, or can we observe them out there? So thank you again to our wonderful speaker. Keep looking at the skies, folks. Now, don't forget, next Thursday, next month, on the first Thursday, the 4th of November, you can join us for our next Skeptics in the Pub. Put that in your diary. And please check out the wonderful range of guest speakers and aliens and who knows what at the forthcoming Skepticon, the Australian and New Zealand Skeptics Joint Convention. You can buy your tickets now. They're very cheap at skepticon.org.au, or just go to skeptics.com.au to find out more. But for tonight from Sydney, Australia, this is Richard Saunders thanking you and signing off.